Now let's go back to our four-stroke spark ignition engine. So that is the last slide that I showed you. So by looking at them, again, we have four strokes that make one cycle: intake, compression, and power or expansion, and exhaust stroke. But now that is pretty complicated. Then we need to simplify that, the realistic processes to more ideal processes to make a thermodynamic cycle. This whole task was done by engineer in Germany whose name is Otto. And he was the first one who came up with this, invented that cycle, which is the base, theoretical base of that spark ignition engine. So what he thought is like this. Now let's take a look at the intake stroke and exhaust stroke. Let's take a look at this part, okay? Then what happens during the intake stroke and exhaust stroke is here, as I make a circle. So what happens in the intake stroke is that we have slightly lower than the atmospheric pressure, and we expand the volume. And during the exhaust stroke, then the pressure inside the cylinder is slightly higher than the atmospheric pressure, PATM. Then it shrinks. Okay. If you really think about the boundary work that would happen during these two processes, we have same pressure and we only change the volume. So even though we have certain different pressures during these two strokes, they are so, their difference is very slight. So we basically can assume that those two processes have the same pressure as the atmospheric pressure. So if we assume this way, then all works that are involved during these two processes basically have the same work. So they can be canceled out in terms of a net work perspective. Okay. So we assume that P constant is at P ATM during this intake process and exhaust process. So then all works involved during these two processes are the same. So we can easily cancel those two processes. So now the conclusion is that, based on this constant and the same pressure assumption during these two stroke processes, we can ignore this intake stroke and exhaust stroke. Okay, so that we don't worry about. Okay. Then this exhaust process only can be replaced by exhaust blowdown. Then remember, what happens in real spark ignition engine is the one combustion process that changes total chemical composition of your working fluid. But we ignore that by assuming the only working fluid involved in that engine is the air, which is an ideal gas. And now, in terms of this exhaust blowdown process, instead of considering that actual gas is exhausted through the exhaust valve, we assume that still air is trapped in the cylinder and piston assembly. But during this exhaust blowdown process, we have heat rejection. Okay, so there are two big assumptions in order to simplify entire real processes of these four-stroke SI engine to ideal thermodynamic cycle. Okay, we call that ideal thermodynamic cycle for four-stroke SI engine as the Otto cycle. And the ideal Otto cycle is based on these two big assumptions. We don't worry about exhaust and intake stroke by assuming that those processes should have the same atmospheric pressure. And now the exhaust blowdown can be modeled in terms of heat rejection. Okay. Then we don't worry about any air coming in, air going out, we assume the whole ideal Otto cycle as closed system. Okay, so that is the biggest assumption. Now, with that discussion, let me go back to the lecture note, and then let's try to see this part. So for the ideal Otto cycle, okay, that is a thermodynamic cycle of SI engine, like more specifically 4-stroke SI engine. Okay. Then, as assumptions for the ideal Otto cycle, as I just explained, both the intake and exhaust stroke occur at PATM. They have the same pressures. Therefore, works involved during these 2 strokes are the same. So we don't really have to worry about these 2 strokes. The conclusion is that then we do not consider the intake and exhaust strokes in the ideal Otto cycle, right? So that is one very big assumption. The second assumption is that instead of thinking about the exhaust blowdown process, which involves certain air flowing out of engine, we assume that this exhaust blowdown can be replaced by the heat rejection process. While air is still inside the engine, there is only heat rejection at the constant volume process. So then, this is heat rejection at constant volume. Okay. Now, so with that, only if you look at this portion, we have compression process. Then as soon as we have ignition and combustion process, then it happens so quickly, the volume doesn't change. So this entire combustion process can be modeled as constant volume heat addition process. Okay, so that is a key portion of the Otto cycle that describes how combustion happens and how heat addition process is involved. And after heat addition process, then we have expansion, which decreases pressure while volume increases. Then this exhaust blowdown can be modeled as constant volume heat rejection process. Okay. Now, so we can clearly summarize our ideal Otto cycle as 4 processes. One is compression process, but now let's talk about the ideal case. The ideal case is that all processes are possibly, if possible, that we can make those processes as ideal or reversible processes. Obviously, heat addition process and heat rejection process cannot be ideal. Okay? But compression process and expansion process can be considered to be ideal, which is isentropic. Yes, reversible adiabatic process, which means isentropic process. That is what you assume for ideal Otto cycle analysis. Okay, so then the first process, which is compression process, is now assumed to be reversible adiabatic or isentropic compression process. Then we have constant volume heat addition process. After this heat addition process, now we have again isentropic expansion process. After that expansion process, then we have constant volume heat rejection process. And that is how we can draw diagrams, schematic diagrams of those 4 processes. Okay? We don't have any valves anymore because that is ideal. We don't care about any flowing in or flowing out of your working fluid. So air is trapped and just experiences compression and heat addition and expansion and heat rejection. So let me just write it down. The basic assumption for ideal Otto cycle analysis is your system is closed system. Okay. Then while piston moves from the bottom to the top, we have isentropic compression process. Then instead of worrying about combustion process, we replace it with heat addition process. And this heat addition process happens while this piston remains its position at the top. So that is constant volume heat addition process. Then piston moves back to the bottom position. And that is isentropic expansion process or isentropic expansion process. Then instead of having exhaust process or exhaust blow down process, while we assume that while this piston stays its position at the bottom, that is center, we have constant volume heat rejection process.